Carry on today with the field effect transistor, section 8.2, the JFET characteristics and parameters. Important section, so please pay close attention. Let's go and have a look in the textbook. On page 371, introductory paragraph, you can mark as I've marked. The JFET operates as a voltage controlled constant current device, as we've seen in the previous section. Cutoff and pinch off as well as JFET transfer characteristics are covered in this section. Right. Now, if we have a look at figure 8.5 on the next page, where it shows the drain characteristic curve of a JFET for VGS is equal to 0. Let's see what happens there. Consider the case when the gate to source voltage is 0. VGS is equal to 0. I can see that VGS is equal to 0. Remember, that's my drain and my gate and my source. So VGS, the gate is connected to ground, so I can see that VGS equal to 0. Ne? This is produced by shorting the gate to the source, as in figure 8.5a, where both are grounded. As VDD and thus VDS is increased from 0 volts, ID will increase proportionally, as shown in the graph of figure 8.5b, between points A and B. In this area, the channel resistance is essentially constant because the depletion region is not large enough to have a significant effect. This is called the ohmic region because VDS and ID are related by Ohm's law. It should look familiar. If you remember in the previous chapters, the BJT that we've discussed. Only in this case, my curve is of ID against VDS. And I can see here they're talking about this section here between points A and B. As I increase VDD, it's in the ohmic region, and ID and VDS is related according to Ohm's law. Alright, what happens after that? If we turn the page to page 372, those sections also very important. First one's called their pinch off voltage. Now you have to pay close attention. For VGS is equal to 0 volts, the value of VDS at which ID becomes essentially constant, point B on the curve in figure 8.5b is the pinch off voltage. You can see it here on that curve. Here's point B, and you can see here where this broken line here, that's V, lowercase letter p, pinch off voltage. Alright, I will explain more about the pinch off voltage as we go along. For a given JFET, V pinch off has a fixed value. Alright, so any type of JFET, V pinch off has a fixed value, which I will get from the data sheet as well. As you can see, a continued increase in VDS, above the pinch off voltage produces an almost constant drain current. This value of drain current is IDSS, drain to source current with the gate shorted. That's the maximum current for this device. And is always specified on the JFET data sheet. Alright, so that's the maximum current. IDSS is the maximum drain current that a specific JFET can produce regardless of the external circuit. Now if we compare this with the BJT, what happened with the BJT? What determined the maximum current through the transistor? The external circuit, can you remember? When I had to calculate IC SAT, it was determined by the supply voltage and resistance around that circuit. In the case of the JFET, it is maximum current for that specific device, regardless of the external circuit. Okay, please take note of that. and it is always specified for the condition VGS is equal to 0. So like in this condition, we've seen here that VGS is equal to 0, and in this condition I can get the value of IDSS, maximum current through a specific JFET regardless of the external circuit. Okay, and then as I increase VDS, I can see there then that current remains essentially constant. This graph looks very similar to the BJT. Alright, then of course I reach a point where it should not be operated, of course, which is the breakdown point, and the current increases dramatically, and actually the device is in breakdown. But that is discussed in the next section there with the heading breakdown. As shown in the graph in figure 8.5b, breakdown occurs at point C when ID begins to increase very rapidly with any further increase in VDS. Breakdown can result in irreversible damage to the device. So JFETs are always operated below breakdown and within the active region, constant current between points B and C in the graph. Alright, the next point we also discussed basically, VGS controls ID. Let's connect a bias voltage now, VGG. Remember we had it on ground, on 0. So if I connect a bias voltage now, as shown in figure 8.7a, actually let's just go back to 8.6. Didn't show you 8.6 yet. Remember where it was grounded? When VG is equal to 0, ID is equal to 0, then the B part there, ID increases proportionally with VDS in the ohmic region. Alright, that is between points A and B. And then on the picture figure 8.6c, when VDS is equal to V pinch off, ID is essentially constant and equal to IDSS. You can see there's my maximum current is now reached with the voltage applied. You can see there is certain voltage, and then in the last picture I still have the value of IDSS although I increased the value of VDS. Alright, here a whole family of curves again, the same as we had with the BJT. You can see now that I am biasing. My VGS is not at 0 anymore, so I can adjust it. It's a variable power supply. And remember, when VGS was equal to 0, maximum current for this device. Maximum current that I get is for a specific JFET. I get from the data sheet regardless of the external circuit. Now I start to increase this biasing voltage. Remember, it's reverse biased, eh? So you can see as I increase VGS minus 1, you can see that the current becomes smaller, ID becomes smaller, né? And so forth. As I carry on, it becomes smaller and smaller and smaller. Alright, until I've reached the point, as we've seen, discuss that now, VGS equal to VGS off. What happens at this stage? That's when the two depletion regions touches each other and the channel is completely closed and no current flows through the device anymore, né? So remember again, no biasing, maximum current, because then the channel is open. As I start biasing, I'm starting to close the channel down until it's completely closed down and ID becomes 0. Alright, what I want to point out here as well, let's just read here. As VGS is set to increasingly more negative values by adjusting VGG, a family of drain characteristic curves is produced as shown in figure 8.7b. Notice that ID decreases as the magnitude of VGS increases to larger negative values because of the narrowing of the channel. Also notice that for each increase in VGS, the JFET reaches pinch off where constant current begins at values of VDS less than V pinch off. The term pinch off is not the same as pinch off voltage. You must be very clear on this. If we go and look at this graph, where did we find V pinch off? V pinch off, we determine where VGS was equal to 0, and I've got my maximum current, so that was point B on the previous graph, né? There, that point B, just as it starts to become constant, I get a value. In this example, let's say V pinch off is equal to plus 5 volts. But of course, as I start to bias, you can see then I get another pinch off. Now this is pinch off when VGS is equal to -1. It is not V pinch off. It's pinch off voltage at VGS of -1. You must be clear on the difference between the two. Okay, so also what you can see is that that value, because of the curves, becomes smaller. Alright, so depending on where we are on the curve, I can see that the pinch off voltage becomes smaller, but V pinch off is determined at VGS equal to 0 at IDSS, maximum current. Alright, so make sure that you distinguish between those two. Here again, just to make sure, VGS controls ID. When VGS is equal to 0, in other words, no biasing, VDS is larger or equal to V pinch off, then ID is equal to IDSS. Remember, now the channel is completely open. You can see there, VGS is equal to 0, maximum current flows through this device. Né? Now I start to increase the biasing voltage, VGS, and I can see that the current now becomes smaller because the depletion region starts to grow. The channel becomes narrower. And keeps on happening as I increase VGS, current still becomes smaller, up to a point where I reach VGS off. Where is VGS off? That is where the two touches each other, channel is closed, no current flows through, and I can see that on my ammeter that no current is flowing through this device. Alright. That brings us to the point on page 374, cut-off voltage, on just below figure 8.8. The value of VGS that makes ID approximately 0 is the cut-off voltage. VGS off, as shown in figure 8.8D, just below that figure. No, that was the figure that we just looked at. The JFET must be operated between VGS is equal to 0 volts and VGS off. For this range of gate to source voltages, ID will vary from a maximum of IDSS to a minimum of almost 0. Just a small leakage current. No, it should be 0. As you have seen, for an N-channel JFET, the more negative VGS is, the smaller ID becomes in the active region. When VGS has a sufficiently large negative value, ID is reduced to 0. This cutoff effect is caused by the widening of the depletion region to a point where it is completely closes the channel, as shown in figure 8.9. See, there we can see it. At the point VGS off, now my biasing was large enough to make these depletions regions large enough so it closes the channel completely and no current can flow through this device, and I can see it on my ammeter as well. Alright, another important fact which you must please mark NB on page 375, the comparison of pinch-off voltage and cut-off voltage. There's a comparison that you must remember. Mark this section NB. Perhaps I can just show you, alright, now I'll show you later. As you have seen, there's a difference between pinch-off and cut-off voltage. There's also a connection. There is also a connection. Just see if I can't see it here. It will be a bit more clearer in a picture that we get to later, but if I can refer back to 8.7, that perhaps you have noticed by now. On this example, can you see that VGS, which is equal to VGS off, it's equal to minus 5 volts. But look at the value of V pinch off, plus 5 volts. Alright, but I will show it to you again in a later graph. Anyway, back to the textbook. The pinch off voltage is the value of VDS at which the drain current becomes constant and is equal to IDSS, and is always measured at VGS is equal to 0 volts. However, pinch off occurs for VDS values less than V pinch off when VGS is non-zero, as I've explained to you earlier. Now don't get confused between pinch off voltage, which are voltages where I started to bias already. Okay, remember, V pinch off is where there's VGS is equal to 0. The other pinch off voltages is not the same, of course. However, pinch off occurs for VDS values less than V pinch off when VGS is non-zero. So although V pinch off is a constant, the minimum value of VDS at which ID becomes constant varies with VGS. But, last paragraph, important. VGS off and V pinch off are always equal in magnitude but opposite in sign. Underline that sentence. That's exactly what I've shown you there in that previous graph. And this is also important. A data sheet usually will give either VGS off or V pinch off, but not both. But of course, now we already know, if the data sheet gives me V pinch off, then I know VGS off is the same magnitude, just the polarity will be different. It will be a different sign. But I will show it to you more clearly in a graph that's still coming. However, when you know the one, you have the other. For the example that they're giving here, if VGS off is minus 5 volt, then V pinch off is plus 5 volts. Anyway, let's have a look at example 8.1. For the JFET in figure 811, VGS off is minus 4 volts, IDSS is equal to 12 milliamps. Normally these values will be given, but I will explain later as well. Determine the minimum value of VDD required to put the device in the constant current region of operation when VGS is equal to 0 volts. So look at the solution. The very first statement that he makes is, since VGS off is minus 4 volts, V pinch off is 4 volts. So the minimum value of VDS for the JFET to be in the constant current is VDS is equal to V pinch off is 4 volts. In the constant current region with VGS is equal to 0 volts, ID, the current that flows to the device, will be equal to the maximum current that flows through. Of course, VGS is 0. There is no biasing being done, and in this case it was given as 12 milliamps. Then the drop across the drain resistor, Ohm's law, VRD ID times RD, 6,72 volts, and then Kirchhoff's law, it always boils down to Ohm's laws and Kirchhoff's laws. VDD is equal to the volt drop VDS and the volt drop over RD, 10,7. So this is the value of VDD to make VDS equal to V pinch off and put the device in the constant current region. Alright, let's carry on. Example 8.2 on the next page. This is also important to note. You can perhaps put an NB there. A particular P channel JFET has a VGS off of plus 5 volts. Plus 4 volts. P channel, remember I have to distinguish between an N channel and a P channel. The N channel, negative biasing, negative voltage. P channel has got to be positive. I will show you later again. What is ID when VGS is equal to 6 volts? What did they say? VGS off is plus 4 volts. In other words, VGS off means ID is equal to 0. Do you agree? So if I increase the reverse biasing voltage, can it become more off? It will still be off, ne? Okay, so it will still be off, ID will still be equal to 0, but they tell you there. The P-channel JFET requires a positive gate to source voltage. The more positive the voltage, the less the drain current. When VGS is equal to 4 volts, ID is equal to 0. Any further increase in VGS keeps the JFET off, so ID remains 0. Of course, no. Remember that. Okay, the next section there is the JFET universal transfer characteristic curve. I'm going to show you how you have to be able to draw this curve as well, but I will explain to you now. You have learned that the range of VGS values from 0 to VGS off controls the amount of drain current. For an N-channel JFET, VGS off is negative, and for a P-channel JFET, VGS off is positive. Because VGS does control ID, the relationship between these two quantities is very important. In figure 8.12 is a general transfer characteristic curve that illustrates graphically the relationship between VGS and ID. The curve is also known as a transconductance curve. Alright, let's have a look at that curve. Again, ID is VGS, and I normally get these values from the data sheet. What do I get from the data sheet? IDSS. That is when VGS is equal to 0, of course. No. Maximum current is flowing through this device, so I can already plot the point IDSS, maximum current for this device. VGS off, also get from the data sheet for a specific device, but it might also be given as V pinch off. Then I know it's the same magnitude, only the polarity is different. Okay, so I can plot those 2 points already. But I'm going to show you now there is a formula to determine the values of ID for specific values of VGS. You can imagine now, I have to determine for specific values of VGS, I have to determine values of ID so that I can plot that point. So I have to be able to plot various points on this curve to be able to draw this curve. Alright, later on we're also going to draw a load line so that we can determine the Q point and so forth. So it's important. Another thing that is important that you have to keep in mind, which they don't show an example in here, although they told you, we know for an N channel it was negative VGS. No. What is the P channel going to look like? Isn't it? It's going to look like that, positive. So I'm going to have a positive VGS value. That's why I said earlier when we started to discuss the JFET that you have to be able to distinguish, especially from the symbols, if it is an N channel or a P channel. Otherwise you're going to draw the wrong transfer characteristic curve. Alright. Anyway, let's refer back to the textbook. If I read there below figure 8.12, we've already established there that they say there, notice that the bottom end of the curve is at the point on VGS axis equal to VGS off, and the top end of the curve is at the point on the ID axis equal to IDSS. This curve shows that ID is equal to 0 when VGS is equal to VGS off, and ID is equal to IDSS when VGS is equal to 0. Alright. Then there are values in between. They say ID is equal to IDSS divided by 4 when VGS is 0,5. But don't worry too much about those. We're not going to use it. Two important ones are the top and bottom points. The transfer characteristic curve can also be developed from the drain characteristic curves by plotting values of ID for the values of VGS taken from the family of drain curves at pinch off, as illustrated in figure 8.13 for a specific set of values. Alright, let's have a look. Maybe it will become more clear when we look at this. We know now to draw the family of curves for the JFET. VGS is equal to 0, got the ohmic region, and we know as soon as the current starts to become constant, what is that point called? V pinch off, nee. So we've got V pinch off there, and we know that value is IDSS. That's V pinch off. Alright, of course we get pinch off voltages for other values of VGS as well, but that is not V pinch off. Also, what we have learned, V pinch off is the same in magnitude as VGS off. And here I can see it. I can see VGS off is -5, and although I didn't draw it very straight, I can see V pinch off is equal to 5 volts. Okay, here I can see it very clear with this combination of these curves. Of course, when I ask you to draw the transfer characteristic curve of a JFET, you don't have to draw this whole family of curves as well. I'm just interested in the transfer characteristic curve. Okay, how do I plot it? I need something. If you go back to the textbooks on page 377, equation 8.1, that is what I need to be able to calculate values of ID for different values of VGS. So what will I normally do? VGS voltages normally fairly low, 4, 5, 6, 7, 8, 10 volts or whatever. So I would do, as they've done here, do it in steps of 1 volt. You can see it's -1, -2, -3, and so forth. Then I go and calculate the values of ID using this formula. ID is equal to IDSS in brackets 1 minus VGS over VGS off squared. Make sure that you know how your calculator works so that you don't make calculation mistakes. Okay, that's what usually happens. Alright, so if I look at this formula, what do I know? IDSS given or from the data sheet. VGS off or V pinch off given. I want to calculate the value of ID, and I will calculate it at various values of VGS. So I will put in this formula IDSS, which is given, VGS off, which is given at various values of VGS. As we've seen on the curve here, I will do it in steps of 1 volts normally. -1, -2, -3, and so forth, and then I get the value of ID. Let's have a look at an example. Example 8.3, the bottom of the page. The partial data sheet in figure 8.14 for a 2N5459 JFET indicates that typically IDSS is 9 milliamps and VGS off is -8 volts maximum. We will have a look at the data sheet just now, where you will say, you can see there why they say typically and why they say maximum. We give various values of the JFET for a specific parameter. Using these values, determine the drain current for VGS is equal to 0 volts, -1 volts, and -4 volts. So, for this example, for specific values of VGS, not specifically to draw the transfer characteristic curve. So, for VGS, I know ID is equal to IDSS is 9 milliamps. Just put the values in the formula. At -1, then I can see that ID will be equal to 6,89 milliamps. For VGS at -4, now you can see that the value of VGS is now placed in there, -4 divided by the -8 volts, which has been given for VGS off, and 9 milliamps. So it's as simple as that to use this formula to determine the different values of ID. But now you can see by using that formula, I can draw this curve. I can calculate these values of ID for these specific values of VGS by using that formula, 8.1. Okay. Because we will see later on, depends on what kind of problem you have to solve. I will sometimes give you the transfer characteristic curve. But sometimes I ask you to draw the transfer characteristic curve and use the transfer characteristic curve that you have drawn to also show me the graphical analysis to determine the Q point and so forth. Okay, so you have to be able to draw the transfer characteristic curve, and you have to be sure which one are you doing, N channel or P channel. I've asked so many students to do the P channel, and because the N channel is shown in the book, they draw me the N channel. Although they tell me that VGS off is a positive voltage, they still draw it that way. Okay, so please make sure that you don't make that mistake. Okay, on the next page, the partial data sheet. You can just, it's not very clear on the screen, but you can follow there in the books just to see where the values of VGS and IDSS and so forth is given. VGS off, for instance, for those three devices, you can see it's it's for the 2N5, 4, 5, 7, 5, 8 and 5, 9, 3 devices, and for the MMBF 5, 4, 5, 7 and so forth. But you can see when you go and look at VGS off, it gives you a minimum and a maximum. That's why in the question they said VGS off in brackets is given as a maximum. Alright. For those specific devices. So you'll have to make sure which device you are working with. A bit lower on underneath the on characteristics, there's IDSS for the three different devices, and they give me a minimum, a typical and a maximum value. Can you remember in the example they said typical value? So if I ask you a question and I say find for this device the typical value of IDSS, then you must read for that value, not the minimum, not the maximum, then of course I told you the typical value, or the minimum or the maximum as I've told you. Ne? Or in the case of VGS off, I will ask you maximum value. So make sure about the values that you have to read from the data sheet. Alright, then the next and last section of the parameters, the JFET forward transconductance on page 379. The forward transconductance. The forward transconductance or the transfer conductance, GM, is the change in drain current, delta ID, for a given change in gate to source voltage, delta VGS, with the drain to source voltage constant. It is expressed as a ratio and has the unit of Siemens. Now if I go and look at that formula, GM, I can see it's current divided by voltage, which is the reciprocal of resistance. Ne? R is equal to V over I, isn't it? Now this is I over V. Okay, that is Siemens. That's a forward transconductance. Other common designations for this parameter are GFS and YFS, forward transfer admittance. But we will discuss this later in chapter 9. GM is important in field effect transistor amplifiers as a major factor in determining the voltage gain. But we will discuss it in chapter 9. Because the transfer characteristic curve of a JFET is non-linear, GM varies in value depending on the location on the curve as set by VGS. And it's clear if you go and look at figure 815. We've seen that the formula says GM is equal to delta ID divided by delta VGS. And because of the shape of this curve, I can see here that the value of ID is much larger than the value of ID at the bottom of the curve. Alright? And over here, I can see there's also a change in VGS, depending on where. So I can see already that the value here will be larger than the value here. Alright, because of the shape of the curve. Anyway, a datasheet normally gives the value of GM measured at VGS is equal to 0 volts, GM 0. For example, the datasheet for the 2N5457 JFET specifies a minimum GM 0 or GFS of 1000 micromhs. Now the mho is the same unit as a Siemens, and a mho, can you see, is just ohm backwards because it's been flipped around. Né? That's what a mho is. Same as Siemens, with a VDS of 15 volts. Given the GM 0, you can calculate an approximate value of GM at any point on the transfer characteristic curve using the following formula, equation 8.2. GM is equal to GM 0, brackets 1 minus VGS over VGS off. Not squared though, as in the formula to calculate ID. When the value of GM 0 is not available, you can calculate it using values of IDSS and VGS off. The vertical lines indicate an absolute value, of course, no sign. Let's have a look at the examples. The bottom of the page there. The following information is included on the datasheet in figure 814 for a 2N5457 JFET. Please go and check that you can find these values on the datasheet just to get some exercise how to use the datasheet. Typically, IDSS 3 milliamps, VGS off minus 6 volts maximum, and GFS max 5000 microsiemens. Using these values, determine the forward transconductance for VGS minus 4 and find ID at this point. Solution on the next page. Just use the formulas. The formulas are supplied with the tests and the exam, but you still have to know which ones to use. Né? Alright, GM 0 is equal to GFS 5000 microsiemens. Use the equation to determine GM. Just put the values in. Next, to determine ID, just use the values again and determine the value of ID. Equation 8.1. Alright, the input resistance and capacitance. As you know, a JFET operates with its gate to source junction reverse bias, which makes the input resistance at the gate very high. The high input resistance is one advantage of the JFET over the BJT. Important. JFET datasheets often specify the input resistance by giving a value for the gate reverse current IGSS at a certain gate to source voltage. The input resistance can then be determined using the following equation, where the vertical lines, of course, again means the absolute value. So Rn, absolute value of VGS over IGSS, and they give you an example there. Example 8.5. Certain JFET has an IGSS of minus 2 nanoamperes for VGS of minus 20 volts. Determine the input resistance. Just apply the formula, and please note that it's not 10,000 mega ohms. It's an American book. That is 10,000 mega ohms. They're not using the metric system. AC drain to source resistance. You learned from the drain characteristic curve that the buff pinch of the drain current is relatively constant over a range of drain to source voltages. Remember, that was from between points B and C. Therefore, a large change in VDS produces only a small change in ID. The ratio of these changes is the AC drain to source resistance of the device, R, X and DS, and it's determined by that formula. Alright, that concludes this section. So please, important to read through the section, make sure that you understand, work through the examples, true false quiz, spelled wrong again, circuit action quiz self-test, and do the relevant basic problems to this section, which is now up to 15.